I'd like to introduce the next speaker. We actually have Alan Frederick here today to talk about Mars electromagnetic radiation shielder.
Good afternoon, everyone. My name is Alan, and I'm part of a team which comprises of myself, Vinod, Ajit, and Bhuvanesh. And we worked on a concept which is the Mars electromagnetic radiation shield. Now, a lot of people over the years have designed many different ways of building a habitat on Mars. But the fundamental problem that we all face is that the radiation exposure that humans face on Mars, or even when they travel through space. So fundamentally, there are three different types of radiation that we experience. The first is galactic cosmic radiation. Second is solar flares. Third is X-rays. The first two are charged radiation. So there is a way that we have designed to bypass the radiation. So the first thing is to protect the humans from the effects of galactic cosmic radiation and charged solar flares. And the second objective is to protect the habitat structures from the effects of radiation. And the third is that while having a localized radiation protective atmosphere, we can use it to build a local biosphere on the habitat. So this is the first literature survey that we based on study upon. And it was done, it's called Space Radiation Superconducting Shield, SR2S. And they devised a system where they had a toroidal magnetic radiation shield in order to protect the occupants in a spaceship while traveling through space. So this was the model which they used. And this was also used, the design was also proposed to be implemented upon aboard the ISS. So titanium magnesium diboroid was actually the superconducting coil which was used. And the density and the current density and conductor length are mentioned here. So the methodology. So the shielding power was first determined by this equation, psi is equal to m naught, where m naught is the mass of a proton, q is the charge density, c is the velocity of light, gamma is the Lorentz factor, and phi is the angle of incidence for the charged particle. And while we calculating the Lorentz factor, we have gamma is equal to 1 by root of 1 minus v by c whole square. So mass of a proton is 1.6 in 10 power minus 27. Charge density of a proton is 1.6 in 10 power minus 19 coulomb, and the velocity, the speed of light is 3 into 10 power 8 meters per second. So calculating the Lorentz factor for different velocities of the particle, of different percentage of light, we get various Lorentz factors. So this is basically an entire table from all the way from 0 to 98% the speed of light, and across different angles of incidences, right from 30 degrees to minus 90, where 90 has the highest effect on the radiation shield. So what we did was we found out for 80% the speed of light, and for the minus 90 degrees angle of incidence, the psi value was 8.35, which is denoted by Tesla meters. So when we put that into the formula, psi is equal to integral of magnetic field strength and dr, which is the derivative of radius, which is equal to m naught by q, and the formula goes that. So Ri is the internal radius of the magnetic, the toroidal radiation shield. Now you might be wondering why I'm mentioning radius, internal and external radius. The ideal shape of this electromagnetic radiation shield is a solenoid, but a solenoid in the shape of a toroid, like a donut. So that is the design we propose. So Ri is the internal radius of 10 meters, and the external radius is 12 meters. So this is just a sample problem that we took on to build, and the habitat can be of any shape and any size, and all we have to do is just vary the values over here. So if the velocity is 80% the speed of light of the charged particle, and the gamma is 1.67 at the phi is equal to minus pi by 2, which is minus 90 degrees. So shielding power is 8.35 Tesla meters, as given in this table. So using these equations, we can calculate the shielding power strength required to protect the inhabitants of the habitat from would be around 4.15 Tesla. Then we put it in the next equation, psi is equal to mu naught by into NIH divided by 2 pi into ln of Re by Ri, where n is the number of turns on the solenoid, h is the height of the entire radiation shield, and mu naught is the permeability of free space. When we substitute the equations for phi is equal to minus 90 degrees, we get the current requirement to be 4.1 kiloamps. That is the power requirement that is required to keep this thing functioning in order to protect it against charged particles traveling at 80% the speed of light, coming at the angle of incidence of minus 90 degrees. So this is the design. So we have rectangular toroid. The reason why we went for a rectangular toroid is that a rectangular toroid can be implemented as walls of the particular structure that we're talking about. So if we have a particular habitat, we can use these toroid as standing structures or support mechanisms for building walls. So it can be implemented just as an air core structure, or you can build composite material. You can use composite materials for walls. Or the other alternative is to use metals mined from the Martian soil and have a ferrite core implemented into this thing to increase the power of the magnetic shielding power. So this is the design of our toroidal magnetic shield. And the coil material. Now, there is a lot of speculation as to what material that we can use. Now, using copper is obviously not an ideal solution because of the weight involved and the cost of space travel involved in carrying such a heavy material. So the material that we chose was carbon nanotubes, and the specifications are given over here. The density is 1.6 grams per centimeter cube, 1,000 times more conductive than copper, 100 times stronger than steel, 10 times lighter than titanium. And it almost has the same electrical conductivity as copper, and the thermal conductivity is 3,000 watts per meter Kelvin, and the electrical conductivity is 10 to 6, 10 to the power 7 Siemens per meter. So the power supply. Now, I don't have an answer to what exactly is the power system that is going to be implemented, but I can tell you if there was a power system, how can we use that in order to get the required current of 4.1 kiloamps required. So using a step-down transformer, wherein we have a high voltage, low current, and transform it into a low voltage, high current. So a transformer with 6,000 volts AC input, 67 amps, and a 60 turns transformer can give you 10 volts AC output with the 4,000 amps, which is exactly almost equal to 4.1 kiloamps that we require with a 1 turn. So the estimated weight is around 700 pounds. So these are the references, and this is the contact information that you can contact us by to discuss this further. And this was the rover that we had presented on the first day. So if you want to discuss regarding both these things, you can contact us at either of the email IDs. Any questions? Sure.
What typical current is that? Like, what was the parallel in everyday life for something that has a similar current?
Sorry?
The amount of current that your generator, your shield will use. What's a similar value to something that I would know of that uses a similar current?
I'm not exactly sure.
Okay. Just wondering, what's the power requirement?
Yeah, this is this was just basically using, we have an electromagnet because carrying a superconducting magnet all the way to space is quite expensive. Now, carrying a superconducting magnet all the way to space, you have the weight restrictions as well.
Okay, so you're giving up on superconducting and you're just going to keep pushing it through the resistance of the, in this case, the nanotubes, which is, as you say, about the same as copper.
Sure.
It's going to require a huge amount of power.
Yes, it does.
All right. If the power fails for some reason, you have no protection.
Yes, but you do generally, when you have a power system, you also have a backup system too.
And if there's a short or if there's open, which is even worse, you're going to have a huge arc, right?
Yes, but see, the thing is, this was actually determined for 90 degrees angle of incidence. Now, an angle of incidence of 90 degrees is quite rare, and that is the worst case scenario. And on a habitat, which is down on the surface, the angle of incidence is usually around 45 to 60. I mean, you don't usually have 90 degrees right perpendicular to the rectangular toroid. So the current requirements are actually lesser.
But if you go with your nominal requirements, if you calculate the total amount of energy that was actually stored in that magnetic flux while it's in operation,
No.
I'm afraid if somebody were to cut that wire, it would just incinerate the whole piece.
Sure. So the thing is, Any other question? Yes.
So we have a magnetic field around the Earth, right?
Yes.
Because we're actually a very interesting molten rock reactor.
Uh-huh.
We're the biggest reactor in the solar system. And so at one point Mars did have a magnetic field, right?
Mm-hmm.
If you look at the rock, you'll see there's a magnetic structure to it.
Yeah.
And then it cooled down and it kind of cooled off. And so I've thought about trying to restart the magnetic field on Mars and what would it would take. You know, we think about things involved the China syndrome, start a big pile of uranium somewhere and have it melt
Any other question?
Did you have any renders of the potential toroid setup and everything beside the archer?
No. Yes.
So if you have this kind of shielding in your habitat,
Uh-huh.
so there's a big magnetic field.
Uh-huh.
So you can't use anything magnetic like tires inside the.
Yeah, you can, but see, the thing is, if you look at the magnetic field lines of a toroid, so what happens is, so you don't, if you look at, it's basically similar to a solenoid, right? So the field lines are actually inside the coil, and the influence right at the center is rather low when compared to right next to the walls. So there is, there are various studies conducted, but it's still a little vague. But the magnetic field does have effects on the body. But that far outweighs the implications of what we would be facing if we were affected by galactic cosmic radiation. Yes, sir.
If you perhaps say, well, you picked up a steel fork
Okay.
inside the habitat, what would the force be on that fork? I think it would be tough.
It would, but depends on where inside the habitat. And I think with the advancement and the growth of composite materials industry, we would not be using steel forks aboard on Mars.
Titanium forks.
Any other questions? Yes, sir.
So this magnetic shielding would affect charged particles but not neutrals?
No, so that's the thing. So X-rays, we don't have a definite solution. So if you go to in a hospital or something, we have walls of meters of length of lead between MRI machines and the other departments of the hospitals. Or the other option is to use Martian soil and build it underground, or construct walls made out of Martian soil. But that would require many meters of soil, and it would require a lot of moving of the Martian soil. So that is an alternative solution for protection against X-rays. But if there are any advancements, because I think by the time we set up habitats, it's going to be around 10, 20 years. So I think by that time we would come up with the necessary technology to protect us from X-rays as well.
What about
Neutrons,
neutrons? They are not charged.
yes.
They have a very big energy and can be very destroying.
Yeah, sure. So again, same mass. Any mass like a solid soil wall can protect the inhabitants.
This is on Mars.
Yes.
But what about flying to Mars?
So this was actually one of the literature surveys that we had initially discussed. This was actually a study conducted by a different company. So they had developed this system for a spaceship while traveling to Mars.
What company?
This was a space radiation superconducting shield SR2S.
How much could something like that weigh?
I'm not exactly sure. The density is 3,400 kilometers per meter, so depends. Yes.
What thickness of water ice would be comparable to that type of protection?
I'm sorry, repeat your question.
Do you know what thickness of water ice? Say you had an ice dome over your settlement or something.
Okay.
If you had a meter of ice, would give you a similar kind of protection?
Not necessarily, because these are charged particles, so they do affect us. And if we're talking about ice, even if we talk about soil, you would need at least a minimum of 7 to 10 meters of soil. But then again, you have ionizing radiation from solar flares, which is quite hazardous. And this entire system can only partially protect us against solar flares because of their enormous power. But galactic cosmic radiation, we have calculated, and it can protect us with 4.15 Tesla magnetic field strength. Yeah. Any other questions? All right. Thank you so much.